Hello, it's Mr. P again, and welcome to another e-learning video lesson on waves. So we're continuing with section 17.3. Remember in the last part, the last video we did together, we had a discussion of reflection, refraction, diffraction, so different phenomenon of waves that occur when waves interact with different surfaces or travel from one medium to another. So we're going to look at some more properties and more things that occur with waves. So we're going to look at interference, which is when two waves basically collide and interact or interfere, right, therefore with each other. And we'll look at something called resonance, okay, which has to do with vibrations and of waves, and something called standing waves. So let's go ahead and take a look here. So interference is what, as it applies to waves, is when two or more waves collide and combine together. All right. So there's two basic types of interference. There's constructive interference and there's destructive interference, and we'll look at what both of those mean. And so constructive interference, that's the first type of interference. Okay, it's when interference occurs and the new wave that forms is equal to the sum of the amplitudes of the original waves. Okay, so constructive means the waves interfere in such a way as that the resulting wave has more energy. Remember, amplitude relates to the amount of energy. The greater the amplitude or the height of the wave, remember the amplitude of the wave, that's this here. That's basically the height, and that related to how much energy the wave has. Okay, so constructive interference, again, occurs when two waves interact in such a way as their amplitudes add together, and the resulting wave has more energy than the original waves. If we apply this to a sound wave with greater amplitude would actually mean the sound would get louder. All right. Destructive interference. So destructive interference is the opposite. So destructive interference happens when the two waves combine in such a way where the amplitudes of the waves actually are subtracted from each other as they interact. So if this was being applied to sound waves, two sound waves that had destructive interference, the result would have a result where the new sound wave would have a decreased level of loudness, right? When we'll talk more about sound in our next section, but if there's destructive interference between two sound waves, let's use that example. The resulting sound wave would be not as loud. If there's constructive, like we just talked about up above, the new sound wave would result in louder sound, right? Because it would have more amplitude, more energy. Okay, so let's look at some diagrams here that will kind of illustrate what we're talking about. So constructive interference. Again, the waves are going to interfere in such a way as we see here. So here's two waves that are going to interfere constructively, and we can see that they interfere in such a way as their peaks occur at the same time. So basically their peaks are happening at the same time. That's why, let's say, the amplitude, let's say the amplitude's 2 meters on each of these waves. Okay? The resulting wave, when they're combined together in constructive interference, we would just add those together. 2 plus 2, what's that? That's 4. So this wave, for example, would be 4 meters. Okay, so again, constructive interference the waves interfere in such a way as their peaks, right? They occur at the same time. So basically you're adding the amplitudes. You're getting a wave that has an increased amount of energy or increased amount of amplitude. Destructive interference, okay, the waves are what we would call out of phase, which means that where I have a peak on one wave, I have a trough on the other wave that basically cancels the peak out. Okay, so it doesn't always have, this would be totally destructive interference, which means, maybe I had an amplitude of 2 meters here, and the amplitude, of the trough on this one was 2 meters, the amplitude of the peak on this wave was 2 meters. So basically they cancel out, and this is my resulting wave. Notice it has 0 amplitude, right? Amplitude is 0 because the waves interfere in such a way as that the peak and the trough cancel out, right? That's destructive interference. And if we think of like a practical example of this, we think of like the noise canceling headphones. Okay, so the technology, right, it emits sound waves, okay, that destructively interfere with the sound waves around you, okay, and basically they cancel out the noise or the sound that's around you. Okay, so it might emit a wave like the one on top here, and it's going to be out of phase in such a way with, sound waves around you that they're going to interfere destructively and cancel out all the sound. Okay, so that's an example of destructive interference in the real world. All right, so remember, constructive interference, add the amplitudes together, we get a bigger amplitude, more energy. Okay, destructive interference, we have a peak and a trough, okay, that occur at the same time, and they basically cancel each other out. We subtract the amplitudes, and in this case, we ended up with 0 amplitude. Let's go ahead and look at backside here. So the concept of resonance. Okay, so we mainly apply this to sound waves. Okay, so resonance is when an object vibrates. Okay, because again, sound waves are nothing more than vibrations at a certain frequency. We talked about frequency, that's a number of cycles per second. We'll talk more in the sound part of the unit about how pitch and frequency are related. But when an object vibrates by absorbing energy at its natural frequency, that's resonance. Okay? So every object has its own resonant frequency. Okay, so tapping on a glass, the sound you hear is the sound at its resonant frequency. You may have heard a singer producing the exact frequency of a glass, which would cause it to vibrate at its natural or resonant frequency and shatter. Okay, so again, you may have heard that some singers produce a frequency that causes glass to vibrate at its natural frequency and thus shatter. Okay, so that's resonance. Okay, when an object vibrates at its natural frequency. And so when that occurs, we have what we call standing waves. So let me roll this up a little bit and show you what a standing wave looks like. Okay. So here's a standing wave. We notice it just kind of looks like it's in place, right? So a standing wave is actually going to occur when we have interference between two waves, and we'll create what we call a standing wave. And I'll show you an example of how that works in just a moment. Okay, so a standing wave, basically parts of a standing wave, a node is actually where there's no amplitude, so there's actually destructive interference going on there, right? When there's no amplitude. And antinodes, okay, those occur when the two waves are interfering constructively. So again, when two waves are interfering with each other, we have what we call a standing wave that's created. All right, and as I had said, okay, we have interference going on here. So let's say we tied a rope to something, okay, and we shake it the other end of the rope, and the waves travel up the rope and they reflect or bounce off of the chair and travel back down the rope, and therefore we have interference that occurs. Okay, as the starting wave passes through the reflected wave. Okay, so, and then certain frequencies produce a wave that appears to stay in the same place. Thus we call it a standing wave. So let me show you an example of a standing wave. So, again, we see that the wave being generated here, okay, it's initially traveling to the right, but it's reflecting off this object here on the right side, and the reflected wave is interfering with the initial wave, and it's creating, the waves are interfering, and what we can see is that there's certain parts of the wave, like here and here, that have no amplitude. That's where destructive interference is going on. Here, okay, would be where constructive interference is going on. And just let me show you something here. So we can see as the wave travels down, it bounces off, reflects, and the reflected wave is constantly interfering with the incoming wave, and it's creating a standing wave. Okay, so, and again, kind of just appears that the wave's kind of just moving in place, basically. So it's a reflected wave interacting with the initial wave, and then there's constructive and destructive interference going on. The peaks you see are where constructive interference is going on, and the places with no amplitude is where there's destructive interference, right? Where, the waves are interfering destructively, where they're canceling each other out. But again, this would be an example of a standing wave. All right, so a real world example would be the collapse of the Tacoma Narrows Bridge. Okay, so I'll show you a quick video clip of that in just a moment. So the wind provided a frequency that matched the natural frequency of the bridge, and the strong vibrations caused the bridge to collapse. All right, so we'll see that in just a second. Again, standing waves occur when we have incoming waves interfering with reflected waves, and we just have a wave that appears to just kind of be, in place, right? With the peaks being the constructive interference, and then the places with no amplitude being destructive interference. So let's look at an example here of the bridge collapse. So again, what happened was the wind created basically a standing wave on the bridge. So the bridge was vibrating or moving in a wave-like motion at its natural frequency, and we'll see what the result of that was.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
is causing the bridge to
Only at 35
vibrate at
miles
its
an hour
natural
with this
frequency.
blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Alright, so, we could see there that that was an example of resonance, where a standing wave was created, the bridge was moving at its natural frequency, kind of like when glass shatters, it's vibrating at its natural frequency and shatters. So the bridge was vibrating at its natural frequency. The wave going through the bridge was at the resonant frequency of the materials in the bridge, which caused them to, which caused the bridge to collapse. Okay?